All right, so I'm going to put these together, and let's think about our charges. What should the formula of CS and SO4 end up being? What do you think, Broadfoot? Yeah, you got it. Good. Two cesiums. So put that there. Once I get the formula, I'll erase my charges on it. So there we've got cesium sulfate. H2O is always just H2O. Also, I'm going to always put liquid after the H2O as well. After my other salt product, these are all going to be soluble salts. I don't even have to check my solubility rules. If they're part of strong acids and strong bases, they'll always give me, the salt will always be aqueous there. All right, does this one look like it's balanced overall from left to right, the whole equation? I don't think so. I'm going to deal with that cesium first, the CS, because it's really jumping out to me as not being balanced. Vivi, what could I do to balance the CS, the cesium, on the whole reaction? Yeah, that's usually the first one to fix there is the cation from that strong base if they're not already balanced and everything. So that looks good. Cesium looks good there. And then I'm counting my hydrogens. So overall, it looks like I've got, let's see, 2 hydrogens from H2SO4, and then I got 2 more hydrogens from the CSOH. So I got a total of 4 hydrogens on the left. And on the right side right now, I just have 2. What could I do to fix those hydrogens, do you think? Ainsley, what could I do to get more hydrogens on the right-hand side? Yeah, I'll put a big 2 in front of water. And that actually balances the whole reaction for me. So these aren't too bad to balance. It's just you've got some different hydrogens floating around there to keep up with. But that happened on that one because it was a diprotic acid. So that one needed a little more balancing. All right, what's my very last reaction I'm looking at? Maddie, what's the third reaction on the sheet?
CaOH2.
Thank you. Let me just erase this. All right, so this gives us one of the bases with the 2 hydroxides. And what's my acid here, Maddie? HCl. This time they've said base plus acid first. That's okay. All right, do the same thing. Put together the outers and inners, or just make your salt and make your water. The salt's going to be Ca and Cl plus H2O. H2O is a liquid. CaCl, that's AQ for that one. For our salt, let's just double check the charges on there. So what's the charge of calcium, Jonathan? Yeah, +2. And then what's the charge of chloride going to be, Parker? The chloride itself is -1. Yeah, it's a group 17. So what's the formula need to be here? Davis, what's the formula for calcium chloride?
You need to add a 2 to the chloride.
You got it. Yes, CaCl2. All right, now I've got a good salt there, balanced charges. H2O is always H2O. Does this one look like it's balanced overall from left to right? What do you think, Mackenzie? Is this balanced from left to right now? No, it's not. I'm noticing what's jumping out to me is the chloride, right? I got 1 chloride on the left and 2 chlorides on the right. So, AC, what could I do to fix the chlorides and balance this thing?
You add a 2 to HCl.
Yeah, add a 2 to HCl. That's going to do the same thing as before. That gives me 4 hydrogens on the left now. So I can fix that with the water molecule. So, Alice, what could I do to get this balanced overall?
2 on the H2O.
Yeah, 2 on the H2O. So these will never be that bad to balance, but if you have the diprotic H2SO4, or you have one of those group 2 bases like calcium, strontium, and barium hydroxide, sometimes they require a little more balancing, and the water molecule helps to balance that out. All right, so that's acid-base neutralization. What questions do you have about acid-base neutralization? All right. There's one other thing I need us to start talking about today, which introduces what we'll deal with tomorrow. So tomorrow we're going to get into the other type of reaction, which is oxidation reduction. Oxidation reduction reactions, they are often going to involve single replacement reactions, but they'll also include other kinds of reactions as well. And we're going to deal with those by keeping up with oxidation numbers. So I'm going to give this out. This has the activity series again, so this is just the note stuff. It's got the activity series on it. I know I gave that out already, but we're going to review how to use that for these single replacement reactions. And then I think tomorrow we'll start getting into oxidation numbers. So you guys are going to be on tomorrow. You want to read through this stuff about oxidation numbers. It's basically finding charges. When we were trying to figure out what's the charge of Fe, we were finding out iron's oxidation number was +2. But we're going to start thinking about things other than just metals in terms of finding oxidation numbers. We'll find oxidation numbers for oxygen. We'll find it for sulfur. We'll find it for every atom in a compound instead of just focusing on those transition metals. So for all those double replacement reactions we were just looking at, for all of those we were using the solubility rules to decide if a reaction happened if we form the solid product. For single replacement reactions, they're one of the kinds of oxidation reduction reactions. We're going to use this activity series in order to predict whether there's a product. So if a product occurs, then some of those steps will repeat as before. Like you got to make sure charges are worked out, come up with the correct formula. You don't have to worry about AQ or solid so much for these, but then you will balance the whole thing overall with coefficients as your very last step. But using the activity series, it's a pretty simple process. What you want to do is look at the single element. So these are all single replacement here because I have a single, in most cases metal, but hydrogen also gets to act like a metal in these things, plus a compound. So those were the single replacement reactions, a single element plus a compound. This activity series has a list of the metals plus hydrogen in order of most reactive as single elements to least reactive as single elements. What element is at the top of the activity series list? Lithium. That means if you have lithium as a single element as a reactant on the left side, you're going to have a reaction happen with these single replacement reactions. What element is at the bottom of this list? Gold. That means gold as a single element does not make a reaction happen usually, and so that's when you're going to have no reaction. If the single element is lower on the left-hand side, you get to just say no reaction for your answer, and you don't have to worry about balancing or anything like that. So let's practice with a few of these now. Looking at reaction A, what's my single metal in A? What's its symbol there? See the Mn on that side? That's my single element. So I'm going to go to my activity series, and maybe I'll put a little mark with my pen, or I'll just put a little, I'll find Mn, manganese. Be sure you're looking at manganese, not magnesium here. I can't seem to find manganese. Here it is. So I know manganese is kind of a little higher than average, but pretty much near the middle. All right. Then, looking at the compound, you want to find its metal. All right. So in these single replacement reactions, if a reaction occurs, the manganese is going to be able to replace the nickel in the compound. All right, well, I want to find the other metal, so that's nickel. So look on this list. You can put your finger on nickel somewhere here. Oh, there it is. So which one's higher, manganese or nickel? Manganese. Manganese is also the single element. If the single element is higher, I'm just going to put a little note here. I'm going to say Mn is higher than Ni. That means a reaction happens. So if a reaction happens, manganese gets to go in and kick the nickel out. So manganese gets to react and bond with the nickel. I'll deal with charges in a second. Plus nickel gets left all alone. All right, so do we see why the manganese gets with the chloride? Manganese does not get with the nickel. Manganese kicks the nickel out of the compound and it ends up taking its place in a way.
I also don't think it will be able to react to it.
You're right. Yeah, two positive charges are not going to stick together, right? Positive and positive won't stick. These often involve transition metals, and when they involve transition metals, you might be wondering, what's the charge of manganese? I don't know. Go back up to your activity series. We'll make the match on here. We go up to manganese based on this. What charge do they give Mn? 2+. So this activity series also includes the charges in a way. So I know manganese is +2. Chloride is still -1 because it's just old chloride. So what's the formula going to be when Mn gets with Cl here? Yeah, let's put a little tiny 2 after the Cl. Then you balance the whole thing overall. So I'll erase all this junk on this side. Does it look like it's balanced? Yeah. Did I, well, I don't have to answer this really, but I'll just tell you. I didn't need to put a charge on nickel. So when it's solid nickel, and that's what we're looking at here, it doesn't have a charge. So when the single replacement occurs, the single element, just like Mn didn't have a charge on the left side, that just means it's the solid piece of metal. So it's like a solid, shiny piece of nickel, not an ion form. So the single element doesn't need a charge. Put a little note here. Single metal doesn't need a charge. It doesn't have a charge, I guess I'll say. Just like if you've got an aluminum can on your desk there, it's not charged. It's not like statically charged or anything like that because it's just solid aluminum. It's not an ion. All right, let's check the next one. First, identify the metals. All right, looks like I'm looking at copper and I'm looking at chromium. Metals and hydrogen are the things that we're going to compare here. All right, which one's higher here? Is the single element, which is copper, and then we've got chromium. Pavitra, which one's higher on the activity series? Chromium's higher, so that means copper is lower. The single metal is lower, so that means it's not very reactive. If the single element is lower, you just put NR for no reaction. You don't have to put the reason why, but since this is kind of notes, we'll put it. Because copper is lower than chromium. Yes, sir.
So we're writing these, we need to worry about putting there's something solid or aqueous.
For now, that's a good point. Something will change on next week for it. Let's go ahead and do it. Okay, that's it. I'm glad you asked that. Next week that will become more important. I was just taking this one step at a time. For all of these that we do, you don't need to use your solubility rules. Okay. Your compound will always be aqueous. Next week, this will become more important, so let's go ahead and get in a good habit now. Your metal, your single metal, will be solid unless it's mercury, which is a liquid, or hydrogen, which is a gas. So the activity series will tell us what state of matter to put on the single element as well when it's the single one there. They're almost all going to be solids for metals. Yeah, I'm glad you asked that. That's going to be important next week. Compound aqueous, single metal is probably solid. All right, let's do letter C. Find chromium, find nickel. Adam, which one's higher, chromium or nickel? Chromium's higher. So Sydney, if the single chromium is higher, are we going to have a reaction here? Yes, we are. So we need to come up with our reaction for this one. We're going to put, chromium's going to take nickel's place in the compound. So we're going to put chromium with the sulfate. And I'm going to go ahead and put AQ after it. Clean up my page a little bit here. All right, and then what's my second product going to be here? MK, what's my second product? Nickel, and I'll go ahead and put solid by it just like I did before. Then let's think about charges on the compound. So I'm going to go back to my activity series list. What charge do they give chromium Cr as an ion, Kira? Yeah, they call it +3, huh? And then what is the charge of sulfate, Joseph? It's -2, yeah. All right, we got the little 2-3 combo. Quick way to deal with that 2-3 combo is just kind of crisscross those charges. There's a little shortcut for it. So I know I need 3 sulfates and 2 chromiums. I'm going to erase the charges on top there. All right, and do I need to put a charge on nickel? No, the solid, single, metal, they're not charged. All right, let's do one with hydrogen just to finish up here. Let's do PT and HBr. When you have this, it's easy to know PT is a metal. Well, you think of platinum as a metal, and it's on the left part of the periodic table. Yeah.
So can we not balance the first?
Yes, I'm sorry. I got ahead of myself. I wanted to get to hydrogen. Thank you very much. We need to balance that thing, don't we? We'll just finish with balancing this one then for today. So we need to balance this guy. How do I balance the chromiums first? What could I put in front of Cr on the left side? Yeah, let's put a 2 there. All right, then next I see nickel looks pretty good so far, but what about sulfate? How could I balance the sulfates? Yeah, let's put a 3 there. Thank you for reminding me of this. And then what does that make me have to do to the nickels on the right-hand side? Yeah, put a 3 there. Thank you. That's important. That's our last step for all of these. That first one just balanced itself, so I wasn't worried about it. All right, so listen, we're going to pick up with some more of this stuff tomorrow. For your assignment, there's just one more question on that aqueous O2 that you need to finish, and then you need to worry about getting all your lab report stuff to that one lab partner. So that one lab partner, all they're going to have to do tomorrow, hopefully, is put everything, clean it up, maybe save it as a PDF or something if they need to,